There's a force tearing the universe apart right now. It has been doing so for the last 5 billion years, accelerating the expansion of space itself, pushing every galaxy farther from every other galaxy at a rate that is increasing with every passing second. Scientists discovered it in 1998. They named it dark energy. And in the 28 years since its discovery, nobody has been able to explain what it actually is. It makes up 68% of everything in the universe, the largest single component of all of existence, and it is completely unknown. But in May 2026, two of the most powerful observatories ever built aimed themselves at the objects scientists use to measure dark energy, and what they found is forcing a reconsideration of everything the scientific community thought it understood about the tool it has been using to track this invisible force for nearly 3 decades. The objects at the center of this story are called cannibal stars. They are dead stars that devour their companions. Their deaths produce explosions so uniform, so precisely calibrated by nature that for 28 years, scientists treated them as the most reliable rulers in the universe. And now, Vera Rubin Observatory and the James Webb Space Telescope, working in combination, cross-checking each other's data, powered by artificial intelligence running analysis that would have taken human astronomers years, have confirmed that the ruler may not be as reliable as everyone assumed. And if that ruler is wrong, then everything measured with it, including the expansion rate of the universe, the history of dark energy, and the ultimate fate of the cosmos, may need to be recalibrated. To understand what cannibal stars are and why they matter so much, you need to understand what happens when a star dies. When a star like our sun exhausts its nuclear fuel, it collapses into a white dwarf, a dense ball of carbon and oxygen roughly the size of Earth, no longer fusing elements at its core, slowly cooling over billions of years. A white dwarf by itself is harmless and scientifically uninteresting from a cosmological standpoint, but many stars exist in binary systems, 2 stars orbiting each other. And when one member of a binary pair becomes a white dwarf, while the other continues to burn and expand, something extraordinary happens. The white dwarf's intense gravity begins pulling material from its companion star. Gas streams across the space between them and falls onto the white dwarf's surface, accumulating layer by layer. This is the cannibalism, a dead star feeding on its living partner. The process continues until the white dwarf has accumulated enough stolen mass to reach a precise threshold called the Chandrasekhar limit, approximately 1.4 times the mass of our sun. At that exact point, the white dwarf can no longer support itself against its own gravity. A runaway nuclear fusion reaction ignites throughout its entire body simultaneously. The white dwarf explodes in a thermonuclear blast so violent that it briefly outshines its entire host galaxy. This explosion is called a type Ia supernova. And because every white dwarf reaches this limit at the same mass before exploding, every type Ia supernova releases approximately the same amount of energy. That uniformity makes them extraordinarily useful. Type Ia supernovas have been considered so uniform in nature that analyzing their light output tells researchers how far away they are and how fast they are moving due to the expansion of the cosmos. In 1998, 2 independent teams of astronomers used type Ia supernovae to make the discovery that changed cosmology forever. They were measuring how fast the universe was expanding at different points in cosmic history by comparing the brightness of type Ia supernovae at different distances, and therefore different epochs in the universe's past. What they expected to find was a universe slowing down, its expansion gradually decelerating as gravity pulled all that matter back together. What they found was the opposite. Not only is the universe expanding, but it is doing so at an accelerating rate. Something was pushing space apart faster and faster over time, overcoming the gravitational pull of all the matter in the universe. The placeholder name for that something is dark energy. The 2011 Nobel Prize in Physics was awarded for this discovery. And for 28 years, type Ia supernovas, the cannibal star explosions, have been the primary tool used to measure how dark energy has behaved throughout the universe's history. Every major constraint on dark energy's strength, its evolution over time, and its ultimate fate has come from measuring these explosions across cosmic distances. If the explosions are not as uniform as assumed, every one of those measurements is affected. Scientists are now reconsidering their knowledge of these standard candles using artificial intelligence and data from the groundbreaking Vera C. Rubin Observatory. The issue is subtle but profound. The assumption that all type Ia supernovas explode with the same intrinsic brightness has always been a simplification. Astronomers have long known that there is scatter in the luminosity. Individual explosions are slightly brighter or slightly dimmer than average, and corrections are applied based on the shape of the light curve, how quickly the supernova brightens and then fades, and the color of the explosion. These corrections bring the scatter down to manageable levels, but they do not eliminate it entirely. And the question that the new Rubin plus JWST research program is now asking is whether there are systematic variations in type Ia supernova brightness that the existing correction methods are not capturing. Variations tied to the properties of the host galaxies in which the explosions occur, the age of the white dwarf population producing them, or other environmental factors that have been averaged out in previous analyses without being properly accounted for. Scientists are hunting for unknown unknowns, missing ingredients in our recipe of the cosmos that could solve the puzzle of dark energy. The research framework developed to address this problem is called CI-GARS, Combined Inference and Galaxy-Related Standardization. Instead of using spectroscopic observations that revolve around analyzing light signatures, the CI-GARS approach looks at actual images and maps of galaxies to standardize supernova brightness measurements. Rather than correcting supernova brightness based only on the supernova's own light curve, CI-GARS incorporates detailed information about the host galaxy, its star formation history, its metallicity, its stellar mass, its morphology, to build a more complete picture of the environment in which each explosion occurred. The hypothesis is that type Ia supernovas in young, actively star-forming galaxies may systematically differ from those in old, quiescent galaxies, and that these differences have been partially masking the true relationship between supernova brightness and distance. Vera Rubin is the observatory that makes this approach possible at large scales. Every night, Rubin scans the southern sky and detects supernovae in real time, catching them early, when their light curves are just beginning, and in the context of deep, high-quality images of their host galaxies that have been accumulated over months of repeated observations. The artificial intelligence pipeline that processes Rubin's data classifies each transient event, identifies it as a supernova candidate, and immediately alerts astronomers worldwide. Within hours of detection, JWST can be pointed at the most scientifically interesting events for follow-up spectroscopy, confirming the supernova type, measuring its redshift precisely, and characterizing the detailed properties of the explosion in ways that Rubin's wide-field camera cannot achieve alone. The James Webb Space Telescope's specific role in the Cannibal star investigation connects directly to its earlier work on dark matter. JWST studied a region of sky for around 255 hours with its near-infrared camera as part of the Cosmic Evolution Survey, analyzing around 800,000 galaxies to paint a detailed picture of dark matter distribution across cosmic time. The same galaxy images that constrain dark matter through gravitational lensing also constrain the stellar populations of the host galaxies where supernovae occur. When JWST maps the dark matter, halos around galaxies, and simultaneously characterizes those galaxies' stellar ages and metallicities, it provides exactly the kind of environmental context that the CI-GARS framework needs to properly standardize supernova brightness. JWST is not just following up on individual Rubin supernova alerts. Its deep field surveys are building the galaxy context database that makes every Rubin supernova measurement more accurate. The two observatories are not working in parallel. They are working together, each providing what the other cannot, building a combined dataset that neither could produce alone. It is a basic fact in modern astrophysics that we do not know what most of the universe is made of. The familiar objects around us, people, planets, stars, account for only about 5% of what exists. The rest, in theory, is dark matter, which helps hold the universe together, and dark energy, which is thought to be responsible for the universe's accelerating expansion. The terrifying aspect of this situation is not that dark energy exists. It is that it has been the dominant component of the universe for 5 billion years. It is currently tearing apart the large-scale structure of the cosmos at an accelerating rate, and science does not know what it is at a fundamental level. The simplest mathematical description of a dark energy is Einstein's cosmological constant, a term he added to his equations of general relativity, representing a constant energy density inherent to empty space itself, uniform everywhere and unchanging over time. If dark energy is truly a cosmological constant, then its behavior in the future is predictable. The universe will continue expanding forever, the distances between galaxies growing without limit, until eventually even the atoms of matter are pulled apart in what some physicists call a big rip. But the cosmological constant is a description, not an explanation. It tells us how dark energy behaves. It does not tell us what dark energy is or where it comes from. The alternative, that dark energy is not a constant, but a dynamic field that changes over time, known as quintessence, has different implications. A dynamical dark energy field might eventually reverse, causing the universe's expansion to slow and potentially reverse in a big crunch, or it might accelerate further. The distinction between a cosmological constant and dynamical dark energy is exactly what the supernova measurements are designed to test, A new analysis that considered type Ya supernovas, alongside 3 other probes of cosmic structure, found results that shine new light on our understanding of the universe and its expansion. The early indications from combining Rubin's supernova data with JWST's galaxy characterizations and the CIGAR's framework suggest that once host galaxy properties are more carefully accounted for, the scatter in type Ia supernova luminosities changes in ways that affect the inferred dark energy parameters. Whether the effect is large enough to resolve the Hubble tension, the stubborn discrepancy between different methods of measuring the universe's expansion rate that has persisted for a decade, or whether it reveals evidence for dynamical dark energy rather than a simple cosmological constant, is a question that requires the full Rubin survey dataset to answer definitively. That dataset will accumulate over the next 10 years. What Vera Rubin and James Webb have confirmed together is not that dark energy has been measured incorrectly. It is that the measurement can be made better, that the tools used to measure it for 28 years contain systematic uncertainties that were not fully accounted for, and that the combination of Rubin's wide-field survey power and JWST's deep characterization capability, linked by artificial intelligence that can process and classify millions of events per night, provides a path to measurements precise enough to finally distinguish between the cosmological constant and dynamical dark energy. The universe's most terrifying secret, the force that makes up 68% of everything and is pulling the cosmos apart at an accelerating rate, is not more terrifying because of what Rubin and JWST have found. It is more precisely known, and in science, a precisely known mystery is always the first step toward an answer. The cannibal stars will keep exploding. Rubin will keep watching. JWST will keep following up. And somewhere in the next decade of data, the answer to what dark energy actually is may finally emerge from the light of dead stars devouring their companions across billions of light years of expanding space. The Hubble tension itself deserves a moment of explanation because it sits at the center of why the cannibal star recalibration matters so much. The universe's expansion rate, the Hubble constant, can be measured 2 ways. The first uses the cosmic microwave background, the faint afterglow of light from 380,000 years after the Big Bang, to infer what the expansion rate must be today based on the universe's early conditions. The second uses type Ia, supernovae, and other local distance indicators to measure the expansion rate directly in the nearby universe. The 2 methods give different answers, disagreeing by approximately 5 to 8%, a discrepancy that has persisted through increasingly precise measurements on both sides and cannot be explained by measurement error alone. If the type Ia supernova measurements are systematically biased by the host galaxy effects that the CIGAR's framework is now correcting for, the local expansion rate measurement could shift in ways that reduce or eliminate the Hubble tension. Whether the cannibal star recalibration resolves the tension, deepens it, or reveals something genuinely new about the physics of the early universe is the question that 10 years of Rubin data checked continuously by JWST will answer. 2 observatories, 10 years. The universe's most fundamental unsolved problem. The greatest cosmic movie ever made, as NSF director Brian Stone described Rubin's 10-year survey at its July 1st launch, is not only a time-lapse of the sky, it is a measurement of the force driving the universe toward its ultimate fate.